big topic, but we're not going to spend too much time on it. Why is that? I don't know. It seems like you need to use the same kind of techniques that we were using already. So there will be a lot of repetitions, so we're not going to do that. So we want to concentrate on differences to what we have been doing before. And just to remind us, there are many axes along which we can order problems of reinforcement learning. And one of the axes is amount of interaction. With the environment. So you can go to plus infinity, and you can go to minus infinity. So here is batch RL. Here is online RL. That will be the last topic. And somewhere in between sits planning, I think, where you're controlling the amount of interaction in a way. Whatever, I made it up, but I think that, yeah, like that's roughly the picture. So in batch RL, there is no interaction with the environment. Someone else collected the data for us. And given all the data, which usually comes in the form of transition snippets, you want to learn a good policy. And you have the usual problems, and some more. So the usual problem is that, okay, like, how do we compute a good policy given the data that we have collected so far? The computational questions, how much data do we need to get a good policy? It's like statistical efficiency. How good a policy can even be if we are constraining ourselves to, I don't know, computationally and statistically efficient algorithms, and you have really large environments. So there's like approximation errors and like how much you need to blow up approximation error. So there are all these questions. But what's unique about batch RL is really this question of like, okay, there is data and it's passive. It's being collected in some way. But we can sneak in a little bit of the interactive aspect of the problem. Because so we're going to have just data sitting on the disk, but someone needs to collect that data, right? Like, and sometimes you can design the data collection process as well. So that would be somewhere here. It's like, this is the design problem, design of data collection. So to me, this kind of belongs a little bit to batch RL, because sometimes you do have the option of designing the data, and then you should be asking the question, how should I collect the data?
How does this differ than, like, let's say online RL with a warm start? Like, you know, you're given some data, and...
Oh, the online RL would be, with a warm start, would be that once you unleash your system, it learns. In batch RL, okay, so that's a possibility, but that's not what we're talking about. Like, in batch RL, just a warm start. Like, where you start? How good is the policy that you can start from? And then, like, how to use prior data to do some warm-up, that belongs to online RL. Because that's about, like, you know, just online RL, like, just design this thing.
I guess I was curious as to, so the design of the data collection would be like RL, would be warm RL, online RL with a warm start. Like, because you're now asking.
But it's not online RL, it's batch RL. But, okay, so it's like kind of flipped around. I understand what you're trying to say. You could go back and forth between these two,
Okay.
and then you're getting online around, basically, right? Because the data that you collected is now informing how you want to collect more data to get even better. And so the difference between what I'm talking about here and online RL is that are you closing the loop?
Okay.
And if you're absolutely not closing the loop, then that's like, okay, the harshest part, because you're kind of like flying in blind. You need to collect the data, you don't know much, maybe you have some prior knowledge, but that's it. You need to collect data, and then given the data, you just have to act well. And you have no further options for further improvements. There are variations of this problem where people say, I allow you to adjust your policy 5 times. How good can you be? It's like, that's, some people study this problem, so it's fluid. It's like you can travel back and forth between these settings, yes.
I guess in that case, like I was going to say, this is kind of like optimal design, but now we ask for optimal design for the whole algorithm immediately. But like if we just take the policy iteration question, we kind of had optimal design to solve a problem for each policy.
Policy evaluation.
Yeah.
Right.
So if you say 5 policies, then you just do policy iteration 5 times, and I guess it's kind of, you just use the optimal design for that, maybe, I don't know. But it sounds much harder now because you can't roll out your policies
Right,
with the
right.
simulator.
It is like, you're absolutely right. I deliberately used the same word, design. It's okay, I didn't have to make this up because in statistics this is how it has been used forever. So experimental design is when you're thinking about how you're going to collect data. You're designing an experiment, and then you run the experiment, that's the data collection. And so basically you can fall this under statistics as well. Anyway, so there will be 2 aspects to this question, and we're not trying to close the loop here, but there are papers written about this, and there are interesting open questions, so it's like you should know that there are opportunities for doing more. But this is introductory class, so we just stop first step. And like cleaning up the foundations and just like asking the simplest questions, I think most of the gain is usually coming from just like asking the simplest questions anyways.
I have one more. So about this axis, like, what do you define by interaction with the environment? Is it like the real environment?
Yeah.
Because in that case in planning, aren't we in the very left-hand side?
Oh, there we were forming the real environment into the simulator, and like, I don't know, like, you can ignore this if you want. In planning, you are, well, if you identify the simulator, like you ignore simulation errors, or that the simulator could be different than the real environment, then you're really at the fine-grained level controlling how you're collecting data.
But then aren't you more, like, how do we measure this interaction? I don't know, maybe this is just too nitpicky,
But in planning, yeah, it's like, it could be that like, yeah, it's like plus infinity.
Yeah.
So some version of planning could be so that's like that. Like you can fly here and there in the state space, and like that's not like online RL. They're just like plus infinity where you can just execute trajectories.
Yeah.
Online planning, like online access to simulator would be similar to that, right? Okay. Yeah.
Sorry, this is a batch RL problem I've been, like this loop, I remember I was talking, I think, with Nathan Callis, and there were 2 questions that kind of came up. First is, let's say you do this batch RL thing, you design a data collection, but whatever company or whatever person's like, no, we're not going to follow that. We're going to only, like, you design an optimal design for data collection, but a company gives you some data, and then you have to figure out how much of this data maybe was collected to the policy I care about, and then how much of the data was just collected to an arbitrary policy, and should I figure out what policy that was, or is there like some version of the problem?
So this is what, yeah. So there is data with just comes about, you don't even know how it was collected. That was the first topic I wanted to talk about, and that's the topic for which I wanted to project something. But I can just tell you the story. So in the family, Wordle is really popular. So every day, everyone does Wordle. We compare statistics, blah, blah, blah. My family just figured out that someone collected statistics about, like, you know this game, Wordle.
Yeah.
Like, you have to guess a word, an English word, and, like, if you're clever, you're guessing it with fewer guesses. But, of course, there is some luck element as well. Anyway, someone was collecting data. It's just a game. And someone was collecting data about how well people are doing across the world in different countries. And so my kids were telling me that Canadians are really good. We are beating the Americans. And but the Swedish are even better. And I'm like, this is awesome for our class. Because, like, when you hear this, so what does this mean? Someone collected some data, some statistics. In this case, it's like, in a country, people who show up and play the game, on the average, in the long run or duration of the data collection experiment, how many guesses did they need to get the word right? And the data shows that the Swedish average is smaller than the Canadian average, which is smaller than the US average. And it is very tempting to conclude, wow, those bastard Swedish, they are so clever, right? Or the Canadians are just better again than the Americans. But is this really so? Like, what are your thoughts about this?
So you ask in which countries who's playing the game. Like in Sweden are only people who are confident in their English skills, maybe educated, maybe people who really study English playing the game. Canada, this makes sense. Generally, I think even amongst, like, it matches education achievement rates. Maybe US has a more diverse population. I know Canada recently has allowed way more educated immigrants in than the United States. Things like this.
So that there are aspects to this. What other? Okay, so this is in a nutshell. You could call it data collection bias or sampling bias. It's not a designed experiment per se, right? Like when we're thinking about, like, what's the meaning of this average? Does the average mean that, like, Swedish are really better? It would mean that Swedish are better on the average if the experimenter were randomly picking a person in Sweden versus in Canada versus in the US, and they would measure their performance and they would repeat this, and then the data would be, like, representative to the population of the country. But whoever is playing the game. So one aspect of this is that maybe there is some selection bias. Maybe what Alex is saying is that maybe in Sweden, like, more the, like, it's not your native language, why would you play this game? And maybe in Hungary they are really good because they're absolutely far away from English, and only those people who really care about education are going to have enough proficiency of English to play this game. So, okay, there is this selection bias. What other biases come to mind? Yeah.
So I don't know if it's a bias, but if there's this country if there's some country that's, for example, worse than US in terms of Wordle performance, then it's very unlikely that in this experiment they will, like, these samples that we get will actually result in conclude in a better performance than US. But if you have 200 countries, then some of them.
Oh, there is a random effect.
Like
Okay.
multiple hypotheses.
Right. So you're pointing out that, like, even if we had a well-designed experiment, we are randomly sampling these people. So there is a certain chance that, okay, maybe only very few people play in a certain country, and the variance there is really high, and, like, it looks like today that their number is better, but look at the number in 2 months, maybe it's not going. So that's a good point. I'm not sure that that's the point that you wanted to make, but that's a point.
Well, I mean,
Yeah.
So I just want to say that, like, there's this multiple hypothesis testing problem that we're comparing, like, 200
But that comes from the randomness of the data.
Yes.
And like the simplest form of that is that it's just random, right? Like you could have a smaller sample size, a bigger sample size, and especially if you're comparing many, then like, okay, eventually someone might be beating the US even though everyone is slightly worse, but there is some variance.
What's the range of the guesses? Like what's the range of the?
It's
between zero,
six.
Between 0 and 6.
Yeah.
So the max variance would be.
Zero, yeah, 1 to 6, yeah.
Okay, so the variance would be 5 squared. In the sense that if I ran a huffing bound
Yeah,
and I had 1,000 samples, you can
right,
imagine
right. So
that.
the range is 5.
So like yeah, I guess since the variance is high but not too high, if you have 1,000 samples from each country, all your confidence intervals.
Could be that, yeah, but we don't actually know the data.
Yeah.
So it's like my kids were just like saying, oh, the average is this and that. Wow. Okay. Like we don't actually know how many measurements. And today I did my Wordle in the morning, and it gives you some statistics about like where you are on a chart of like, okay, how many other people have guessed with this, and like I did it early enough, and so the statistics was like I'm the, I don't know, the 20th person ever doing Wordle today. It's like, okay. Maybe it just delayed, but like we don't know these sample sizes or like what the statistics was based on. Okay, so that's another good point. Another bias that came to my mind, by the way, is that like depending on my mood, I play this game very differently. So sometimes I'm serious and I just want to get, like the lowest number of guesses. Sometimes I'm just like, let's be playful. Like I'm optimizing for time. If I'm optimizing for time, I have a very different strategy than if I'm optimizing for the number of guesses. So maybe the statistics is telling us that people in different countries have different level of playfulness or like objectives, and so there is all of these things going on. What's the relationship to here is that we have a non-designed experiment, and from that we want to make conclusions. Like we want to draw conclusions. That's gonna be hard. Okay, so in general that's not going to work. It's really easy to construct examples where it's basically what you do is that there is an outcome. Let's say you have a Reddit problem. So I do have an example like this in the lecture notes. And you have arms, and there are Bernoulli outcomes associated with each of the arms. But there is an underlying Bernoulli outcome which is really controlling what the outcomes for the arms is going to be. So it's correlated to that. And the data collection is done in such a way that this hidden variable, which controls the outcomes, also controls which arm you're pulling. Now you can make it as biased as you wish. Right? So if there is some hidden data that will not be recorded, that really governs the choices of the actions, and then you also, the outcome of the experiment, the reward, is correlated with the same hidden data, then everything can flip around. And like the data is worth nothing. If you don't know anything about how the data was collected, I'm sorry, but like in the simplest Bandit setting, you can't say anything.
But let's say you know that 20% of the data was collected according to your policy, but you don't know which data it is. Something like this.
So, okay, so I don't want to go into anything messy like what you're saying. This is just too messy for me. Of course, that's how the real world is going to be. The cleanest thing, and I think that it's just like good to remember that whenever you're thinking about the data collection, what you should be thinking about is that, okay, you're going to run some policy to collect the data. So it's going to output actions, and it's going to have some inputs, and it's going to be embedded in this big environment, and then the environment, I don't know, feeds back the reward. And you can design this part, but you should record everything, like what comes out, what goes in, and then you'll be fine. then okay, then there are questions of statistical efficiency. Maybe you can have a coverage problem. But if you have access to the data that was used to make the decisions, you record that data, you record the decisions themselves, you record the outcomes, you'll be fine. Then it's a question of like, do we have coverage to actually determine the relationship between the covariates, the decisions, and the rewards. It's basically kind of a regression problem, which with biased data collection, and as long as you have the coverage, you'll be fine. But if any of this is not recorded, Z is not recorded, or partially recorded, A is not recorded, something else is recorded. It's very common, for example, it's a common failure mode for many of these things is not to properly record one of these things, right? Like maybe someone forgets to record like a critical variable that determines how decisions are made, for which the outcomes are recorded. Then it's game over. If it was really critical, you can't say anything. Maybe someone forgets to record the actual decision that goes into the system, but they record something else. So for example, you could have something comes out, and then it perturbed, and then that goes into the system. So you record A, but A prime goes into the system. Well, this thing just became part of the environment, which is fine, as long as the next time you have the same box. But if that box is modified, taken away, so this is typical situation when you have an engineered system and something happens here, someone changes that part of the system because it's under their control to change that, they discover a bug. It was changing the actions before. Let's fix the bug. We fix the bug, all the data is gone. Unless you can reconstruct, for example, what the perturbations were, or like whatever, right? Like if you can restore the data, then it's fine. Anyways, so the meaning of all of this is that you just need a causal setup. This is a causal setup where whatever governs the decisions, like that data is fully recorded, the outcomes are fully recorded, decisions are fully recorded, then it becomes a statistical question. If any of this doesn't hold, then maybe you can still do things, but then it becomes a very delicate question of like whether the constellation of the stars is such that you can still do things. You can still fix up things. A lot of times you can fix up things. So this is the subject of theories of Pearl, where he talks about when can you resolve. He has a complete characterization of when can you resolve these identifiability questions, causal things. But we are, instead of doing that, we're just going to assume that we are in this simpler setting. If you're not in this simpler setting, it's just like, okay, fine. Sometimes you can do things fine. Okay.
One final question.
Yeah.
So back to this loop. There was also like an idea, which was like, could this be formulated in a sense almost as a game? I'm a batch RL agent. I design a data collection process, but then it's someone else who executes the policy, and I don't know which part of the policy they're going to execute, but I assume there's some underlying like strategy on which parts of my policy they're willing to execute, which parts they're not, and then part of the interaction is trying to figure out what's the best recommendations I could give, given that I know there's some constraints on which policies will actually be enacted, or which parts of the policy will be enacted. Something like that.
So what would be an example where this comes from?
So like, maybe you're part of like some, like Amazon or some like recommendation company,
system?
and you want the recommender system to figure out the best way to recommend things to people. But there's an engineer, or there's like someone in charge who says, no, I won't let you
an
take.
engineer. It's pick a scenario.
Or like I won't
Just
take.
kidding.
I'm not just going to
Yeah.
recommend random things.
Right.
Maybe only a little bit of the time
Yeah,
for this type
yeah.
of user.
Right.
And so, but the algorithm doesn't
Okay.
know this. It's trying to figure out how can it convince the engineer to best, like, how can it kind of balance this? I need to collect more data, but I know the engine. If I make too many like aggressive
Right.
recommendations that I need to get information, it's going to reject it. So I have to somehow play conservatively. And then one
Yeah,
is
I maybe you can set up something like this,
Okay.
or maybe you can just like discuss with the engineer, like, please follow my advice.
yeah.
Or if they are worried about losing too much money because your data collection is just going to ruin customer experience, then you should dial back on the data collection. I mean, like that's right. Like they have to have some budget if they are really, knowledge is not for free. Then we can talk about like what's the cleverest way of collecting the data. That's the optimal design question. And maybe you want to have multiple stages, blah, blah, blah. And so there are these variations that come into play. So yeah, like you can play around with all of these things.
I guess the high level question was, is this like a constrained optimization problem? You feed in the constraints, or is this more of a game where you have to kind of, I guess that was the best way to formulate this type of problem. I guess in the real world. It is messy. Anyway, those are just.
What do you want to say? Okay, I see that. You had some comment. Okay. Yeah. If I think it's an optimization problem. Data collection is designing a distribution in the face of uncertainty. So maybe there is a worst case element there. Maybe you want to design the distribution in such a way that even with the worst case distribution, the accuracy is best possibly controlled. That's a possibility, right? Like that's a possible formulation. And yeah, actually, I was wondering about whether I should invite Chen-Chen to talk about something like that. Okay, but that's design. Let's move on to a little bit of RL. I don't know. I guess we'll come back to this design question of like, or we can discuss it now. So if you have a controlled system, then the design question is like what policy to run, history dependent. Okay, if it becomes history dependent, it's really an adaptive data collection strategy. Then we're really in the online learning setting, so I think that doesn't count. It has to be a passive strategy because otherwise it's like, yeah, we are just talking about online learning for the sake of learning the best possible policy, and we can talk about it. That's fine, but that's just online learning. There is the passive data collection, and for whatever reason, Amazon or Google or whatnot, like, might demand that you're doing the data collection passively because they're too scared of your adaptive procedure. And they can at least predict. So what's the advantage of a passive procedure? You can run some preliminary experiments and predict how much money they're going to lose on running these experiments, and it's more controllable in a way. So maybe they ask you to design a policy which is not going to change and which is going to be used to collect the data. And so that would be, I think, one way of doing it. Yeah. I think.
Can't you kind of do this in our, like, okay, so you do like a low switch, an algorithm doesn't switch very often, and then you read out the policy and you say, are you okay with this policy? And they'll say yes or no, and then.
That's online already.
But I mean, like, I guess.
You close the loop. We're not closing the loop. We are deliberately, okay, so this is going to be short, like just 4 lectures, not closing the loop. Just hang on tight. You can do this. You don't have to close the loop yet. Yeah. I guess that is the underlying question. Okay, there are 2 questions. Okay, how are we going to collect the data? What policy should we be using? And the other question is going to be, how are we going to use the data? Okay. So for the second, let's start small, because we often start small, which means that, okay, let's start with just thinking about the tabular case. Simplest stochastic control system, control Markov chain. Someone collected some data. What are we going to do with the data? What would you do with the data? What's the simplest?
TD learning.
TD learning. Yeah, if you took Richie's class, then certainly you're gonna use tie coding.
Oh, yeah, okay.
It's gonna be actor critic tie coding and
Thank you.
okay, generalized wave functions. But,
It's a linear MVP.
yeah, if you took my class, it's gonna be some linear MDP. No, it's just tabular.
I guess just learn the model and then use everything you learned.
Yeah, I guess just learn the model. So that just means so what is an MVP? MVP is SAPR, and maybe we have this discount factor, and so we're gonna swap this P to a P hat and the R to an R hat, where the P and a P hat, the P hat and R hat are just simple frequency-based statistics, like averages, right? Like if you had your data and in your data you had, I don't know, SI, AI, SI plus 1, and RI plus 1. Okay, we don't have that because we're going to have triplets. I goes from 1 to n. Then you could count how many times, maybe let's count this, how many times in the data we have seen a given triplet. Okay, so the meaning of this prime is that this is the next state that you have seen, and this is the associated reward. So you can just do this counting, and then the p hat of, I don't know, S prime given S A could be just how many times have we seen this triplet given how many times we have seen just the given state action pair. If that denominator is positive. If it's not, then like, okay, max it with 1.
Oh, yeah.
Now it doesn't, okay, so then this is not a distribution, but like, then you just like replace p hat with an arbitrary distribution. That's
Wait, why is it not a distribution?
then you have to max. Well, like, because you need to sum over S prime and then you want to get 1, but you get 0.
Oh, okay. That's like maybe.
That's also fine. Like, if you have a p hat, which is not a probability kernel, but a pseudo kernel or whatnot, like it sums to below 1, everything still works.
Maybe like case smoothing or something.
Huh?
Case smoothing or something. Right?
Case mean.
Add k to both numerator and denominator.
Then there are multiple solutions. And for R hat, it could just be R hat. SA could be just, I don't know. Just those cases where we were at this state in action and divide by this number. Okay. Take max is 1. So now we have this other MDP. So first of all, what we can see here is that, well, we certainly know that this R hat is going to get close to R and the P hat, what? Yeah, what?
I think mine will be longer. You can go.
Yeah, I just found like why now
capacity learning exists because we cannot get like very well formed results or conclusion for learning, like minimizing the projected Bellman error of S function approximation.
Okay.
I'm just like, what if we do not learn a model? Are there any kind of solutions or results we can make?
Right. So maybe this is the simplest, but are there any alternatives? Yeah, you can run Q-learning. Actually, you can solve the model without ever explicitly writing things in this way. So you can move things around. You can design a stochastic approximation algorithm that converges to the solution of as if you estimated the model, you read out the optimal value function and you take the greedy policy with respect to that. You can design algorithms for doing that never ever try to estimate p hat. Why would you want to do that? I don't know. Maybe it's more interesting when we have function approximation. When we have function approximation, maybe it's a little bit more interesting, like, how are we estimating the model? Like, if the function approximate, if the promise of the person giving us the features was that the features are good for resolving just value functions, then like estimating models, like, okay, then there is a discrepancy. Like, they never promised that the features are gonna be good for estimating a model. Then this model-based approach is like, a little bit itchy. So there we can come back to this question.
How about the memory for the model? I guess we don't care too much about memory.
Yeah, we don't care at the moment too much about the memory. And actually you can be clever about, see, it's like if you don't have too much data, then this is going to be sparse too. Like, there are things like that automatically happen. And then if you don't store the zeros, you'll be pretty good, even memory-wise. I mean, if you have all the data already saved, you can never explicitly store p hat and compute averages just using the data whenever you need it. Yes.
Actually, I don't know the answer to this question, but is this the most efficient way? Is this the most sample efficient method for batch RL and tabular setting is to build an explicit model, or can you show that like in certain settings a model-free approximator would do just as well as a model-based approximator?
That is the question.
Okay, I wasn't sure if anyone answered.
That is the question that everyone should be asking right away. Yes, good. That is the question, right? Like that question makes sense. Like, okay, these other questions also do make sense. Does it unnecessarily use too much memory? Blah blah blah. I mean, a tabular setting is kind of like suspect, anyways. We do this for the sake of getting inside, and not because we believe that someone should be doing this or anything like that. It is more like, okay, we want to understand the structure of these problems, and the easiest starting point to understand the structure and like the inherent hardness of this problem is to start with the tabular setting. If we understand the tabular setting, maybe we do have a chance to understand the linear function approximation setting. That's going to be the next step.
I guess we don't even have that answer in the online setting, do we? For model-based versus model-free in tabular setting?
So you could have so there are multiple ways of posing this question. The way Alex was posing the question, which is, okay, he didn't say it this way exactly, but this is the meaning of it. I think this is what he meant. Like, can we get a lower bound and match it with an upper bound for this algorithm? Because if we can, then this algorithm is sufficient in a way. Statistically speaking, the best possible thing you could do, and then we can talk about whether you can speed it up, we can use less memory, and then we can also ask whether a model-free method would do this.
And when you say lower bound, you mean for this setting, not for this algorithm, not for
Yeah.
model-based algorithms.
It's for it's arbitrary for a setting where someone saves some data, and so here for anything to work. What's important is that the SI prime and RI prime should have the correct statistics. So it's like, okay, I don't know right. Like the probability of SI prime being, like S prime, given SI and AI being S and A should be the right one, and so on and so forth. So these are like statements about the joint distribution. One of the things that you could add or you can remove is that this is, so the joint distribution of the whole data, whether all these snippets are independent of each other or not. If they're independent, life is somewhat simpler, but they don't necessarily need to be independent actually. Most of the tools don't care about whether they're independent. They care about some kind of generalization of independence, which is this martingale noise assumption, which comes about, for example, if this was just a continuous stream of data, but it was cut up into these little snippets. So this SI prime is really SI plus. And then this is the associated reward, and so on and so forth. So it was like single continuous stream of data generated from the Markov chain. The conditional statistics is all fine, and the noise is not going to interfere too badly. The noise still behaves as if it was independent. And that is going to be because we have the Markov property. The Markov property allows us to, forget about like what happened in the past. If you know where you are, the next state's distribution and the reward distribution is completely determined by the current state in action, right? So that was the Markov property. And because of that, for the tools that we use to argue that the empirical transition estimates converge to the true ones, let it be for transitions or the rewards, they don't care about this. I mean, like, you have to use slightly more powerful tools, but it's basically, instead of Hovding's inequality, use Hovding-Azuma. Hovding-Azuma can deal with martingale noise.
So going back to Alex's question, I'm not sure if your answer was that we don't know the answer because we haven't covered yet, or we just like...
We know the answer.
We know the
Like
answer.
the field knows the answer,
Okay,
and
the
we'll
field knows
cover
the
it
answer.
in the class.
Okay.
It's
Right.
coming. I don't know, maybe it's not written up in the lecture notes.
I don't remember, but
It's not. That's why, like, it's.
Huh.
We don't have anything on online RL.
Yeah.
oh wait, sorry, I'm asking for the batch version first.
Yeah, we are talking about the batch version.
Okay.
So his question, we
Yeah.
know the answer to that.
Okay.
And okay, like, spoiler alert.
Do we know it up to H
This
factor?
is-
Up
what?
To the, up to
Yeah,
the
it's
H
H
factor?
cube. No, it's like the exact H factor is known.
Okay.
Lower bounds, upper bounds match. The model-based algorithm is statistically optimal.
And the model free one also matches that? or is
Yeah,
it
yeah,
worse?
I think that like people eventually massage the model-free algorithms up to the point that they almost look like model-based, but
Right.
never mind, they match the lower bound. I
Okay.
think that, yeah,
It's
that's
almost
the
the
case.
same for the online setting.
I'm not completely sure about
In the online, I think in the online
model
setting, Q learning is definitely a factor of H, square root of H worse than the model
Yeah.
based out.
I think you can find some setting in which Q-learning is also optimal, which is the episodic inhomogeneous MDPs, which is a weird setting, and there Q-learning is not losing this age because everyone's losing the age anyway, so Q-learning
Okay.
is not losing it.
Which page is it?
I thought the Chigen in homogeneous one was missing that squared H2.
Okay, maybe I'm
Yeah.
wrong, but like, okay, I have to remove that.
Okay, but I mean, I guess the squared H isn't that important at the end of the day.
Always,
No,
it's
it's the
everything.
problem.
It's everything. A square root age is like,
That's all we care about.
Okay.
yeah.
No, but it is a big problem, I think. I mean, long horizon, right?
Yeah. You don't want unnecessary square root age factors, for sure.
Okay. Well, I guess we'll see the batch result soon.
Yeah, the best result is actually super simple. I'm gonna cover it in the next class, but today we can talk about some preliminary
Okay. Maybe I could find
plans for how to solve this problem. Yes.
Maybe I should ask the question that I was going to ask before Jamie's question finally. Yeah, so this made me think about, at the end of the day, when we try to model this model, we're assuming that reward is following this distribution that only depends on the state and the action, and not the next state. And I think we had
Oh, that
discussion
doesn't
about
matter.
this before.
That doesn't
But
matter.
that doesn't matter at all, because I just remember, like, in Rich's stuff, it's always this probability distribution that gives us, like, the reward and the next state, and then the reward also depends on the next state, like, you know, like it's this joint distribution with it, and maybe you can't nicely decompose it into, is that not problematic? Like, this kind of going back to the general assumption we made at the very beginning.
I think that the answer to this question is that the nicest Markov model that generalizes Rich's version as well, and of course, like this silly one that I'm using here, is when you have a kernel that maps state action pairs to next state reward pairs.
Yeah.
And you can have correlations between the next state and the reward, or not correlations, and it could be complicated. In the case of Rich, it's like weird because it's like the reward is a deterministic function of the current state and action and next state. Why is it a deterministic function of anything? Can't I use just like a Bernoulli noise added to that? Like, that's weird. So very often we take away the noise because like it doesn't matter. But sometimes, like in planning, we were talking about this. There is a stark difference in the query complexity of planning for completely deterministic MDPs and MDPs where only the reward is noisy.
It's not the same for online.
And you couldn't talk about that with that set.
When were we talking about this? I actually don't know.
It was supposed to be Garrett.
Oh.
Garrett was talking about many things. And so there is this separation between. So there is a paper, another paper, which says that for Q star realizability, if the MDP is completely deterministic in the finite horizon setting, you have a polynomial query complexity result. And we do have a lower bound with Gallet, which says that just change the reward to be stochastic. Same setting otherwise. And everything's gone. It's an exponential lower bound.
Right. So having this like Q that describes both, that would capture that general set, but and it also captures this like that the reward is possibly correlated with the next
Yeah.
state as well.
Absolutely.
Does that cause any problems as well? Like
No, never.
usually?
Never.
Never? We don't
Never.
have anything showing that that would
I
be a
mean,
problem?
statistically speaking, in those settings that Gallet was talking about, whether you have other difficulties, yes. In the finite case, in this like,
Okay.
in this silly world, it doesn't matter.
Sure. Okay, now I'm happy.
Yeah. Okay.
We can go now.
Alex.
Oh no, I'm just.
All right. Okay. So what to emphasize is that as you get more samples, if you have some regularity with the data collection, then you can expect that somehow P gets closer to P hat in some well-defined sense, maybe for every state action pair. If you look at the next state distributions, then in L1 norm, they're going to get closer and closer to each other, so there is some constant factor. And if your data set size is bigger, then it's like regularly, uniformly fast. They're getting closer to each other. And you can just use a Hovding's inequality or something like that to show this. And the same holds for the rewards.
Is there a coverage assumption here?
Yeah, there are all kind of assumptions. So to make this rigorous, you would start by saying what is the joint distribution here, and under various, under various settings, you can show that holds. So they're getting closer to each other at the uniform 1 over root rate. So for example, if this was IID, and the next reward distribution are as they should be, that holds. The C is going to depend on logarithmically on the number of state action pairs, because you have to have some union bonds over there. And for this one norm, there is a nice trick to be used.
And this is for all state action pairs? So this is like a
So-
one norm and like and then an element.
Yeah, like you put in under the union bond there. So like if you want for all state action pairs that are such and such close to each other, then you have to apply a union bond over the state action pair. So a log S is going to appear, and here there is an additional S factor. So this is bigger by a factor of S. And the way to remember that is that if you have two probability vectors, the one norm difference between the two is really equal to, we like in a product, the difference between the two vectors times a vector whose magnitude is component-wise magnitude bounded by 1, and so that's easy to see, and it's also easy to see that this supremum is going to be taken at one of the corners. So it's okay, if P was S dimensional, then there is an S here. This X was in RS. So now you can control any of this with just hovering. And because here you have a max over this many, you need a union bound. It's 2 to the S, because that's the coordinate of how many different things there are. So that's like the lottery thing, right? Was mentioned at the beginning, that like someone's gonna win, like you have 2 to the S of these differences, someone's gonna stick out, like how much? Okay, you need to use a union bound to control that, and the coordinate there is 2 to the S. So because of that, you're going to have a log 2 to the S over delta instead of a delta. So that's like S log 2 plus log 1 over that. Okay. So that's the origin of this factor of S. Does it have to be there? Yes, yes. It has to be there. As S gets really large, the variance is really growing with S of this expression. It's like everything becomes Gaussian. You can calculate exactly that this S has to be there. You can't say that. Okay. Nothing really changes if this was. Oh, somehow, okay, so in one sense, nothing changes if this was a single trajectory that was cut up, but a lot changes at the same time. So this n is not going to be uniform anymore, because here it was like, okay, so here this n is actually, I don't know, like it's not really n, but it's how many times in the data you have seen a given state action pair. Okay, so I should have written this NSA, and then nothing changes. So what changes is that, okay, so we see that if we have a way of collecting snippets, so design that allows us to collect snippets, then we can make all of these counts to be equal, so as to make the smallest of them, the the largest, right? If we have a small count here, that means that, okay, there is a wide interval, we can't really expect very good performance. So we want to make the smallest count to be the largest. How can we make that happen? Well, if we have the power to sample anywhere, then we can sample each of the state action pairs equally often. And so n is going to be divided by the number of state action pairs and like that. That's how many samples you're going to have at the given state action pair. That's good. All right. So that will be a design which kind of tries to control for the statistical errors. Another question is like, do you really need to control for these statistical errors or not? A lower bound is going to show that yes, you should. If you didn't have this freedom of sampling at any given state action pair, but you need to follow a trajectory, now we are in a little trouble. Because you can imagine that these counts are going to be governed by what policy you are following. And if you didn't know much about the MDP, it would be really hard to choose a policy that forces the counts to be large for each of the state action pairs. There could be some state action pairs which are visited much, much fewer times than some other state action pairs. Right? So now we have to start to worry about whether this is even a legitimate thing to try if you can only run trajectories. This batch learning maybe is doomed. That's what Rich says. So once we had, I don't know, a workshop about batch learning, and he was in the audience or he was invited or something, and then his whole summary was that, well, batch learning, you're doomed. It's like, forget it.
Yeah, has there been any nice positive results about batch learning outside of companies doing
What do you call nice positive result?
all the lower bounds, which is exponential? Like, is there at least a setting where
That's a nice positive result?
no, are there any nice positive results? Like, you just
Well,
want-
if a lower one tells you that you can't, okay, so you can't have that, so,
well, these are
I mean,
specific.
then,
I wasn't sure if there's like a setting in which like
Well, this one is non-exponential if you can not sample from trajectories.
yeah. So for example, here, if you have the freedom to sample from any state action pair, then like you have beautiful bounds. So all that, I mean, like, it's real. The struggle is real here. Anyway, so I just wanted to tell you that, like, okay, we can random add, these are the problems that come up, and then we can wonder about, okay, is this really doomed? And we'll try to get an answer to that, too. And we'll see that, yes, pretty much.
will we learn about pessimism?
Huh?
Will we-
And then we can jump the pessimism bandwagon and ask ourselves, why are we doing this? And yeah.
So I know I asked because I know we went through that whole pessimism phase in oral theory. I wasn't sure if you got any new insights from there.
I didn't.
Okay.
A lot of people work on this, and they time to time come up with some argument that is supposed to show that pessimism, like being pessimistic in the batch setting, is a sensible thing to do. I think it is a sensible thing to do, but I don't find the current explanations satisfactory. But,
And
so I think the hunt goes on.
And when we say pessimism, it's like looking into the thing that we have the least confidence of, like the state in action or something. Like
No, not the least confidence. So these bonds are telling us, you can reverse this, right? Like one interpretation of these bonds is that, oh, my p hat, can I use my p hat replacing p? Maybe you can if all these counts are big. So that's one interpretation. The other interpretation is that p hat tells you only so much about p. It only tells you that p is this close to p hat, but it could be anywhere. So the pessimism idea is to say that take all possible p's, because we don't know which of the true p is, we only know p hat. That's in our hands, we know that. But you can treat this as a free variable and say that like within this radius, I allow any transitions. And the pessimism comes that then you say, take the MDP that gives the worst value for my, let's say, initial state that I worry about. And so that you're pessimistic about the choice, but reasonable about the choice at the same time, because you're not allowing any transition probabilities, you're only allowing transition probabilities that come so close, so the statistically reasonable or indistinguishable models are all allowed, but amongst those you choose the one which gives you the worst value, and then the worst optimal value. So for every p hat, there is an optimal value, and the worst optimal value. You go for that. That's the pessimistic algorithm. Then you can ask the question, can you compute that? Okay, fine. Or do we have any reason to go with this policy? And then there is a huge industry on people are coming up with newer and newer explanations of why pessimism is good in this setting. I can tell you one reason why pessimism is good, and that is the winner's remorse. You're not going to regret it, because it can only get better. That's obvious, right? But that's a good reason, right? Like if you're starting your policy to your boss, and later on you will run this policy, if it comes out to be better than what you predicted, the boss is going to be super happy. If it goes the other way around, I'm not sure about the future of your job. So this is called the winner's remorse in economics. People notice that it's good to be pessimistic because then later you don't regret it. It's an obvious observation. It's not really a mathematical justification, it's a human justification, right? Like the external circumstances are such that we should love pessimism because it's like that is what is going to be rewarded in this bigger context. So what I don't like about this explanation is that it's not arguing from inside with the math, right? Like it's not telling us that if you follow good old-fashioned statistical principles, then pessimism pops up and like this is the best. Yeah, it's an external choice, but it's nevertheless it's a good reason, right? Like we could even stop at that point because I think for many this is important.
Yeah. I mean, isn't Bachelor kind of like, it seems to be like almost a human problem. Like there are multiple results that say we should, like this is hard, like it's intrinsically hard. You should have some interaction with the world and you have to pay some price, but people nonetheless are like, well, we have to solve this problem, so the solution should be a solution that makes humans happy. There's no like, that's what the problem seems. It seems like a human problem.
It's like we create this problem for ourselves most of the time. But okay, so sometimes it's really hard to run experiments on the climate or whatnot. It's like people are scared if you say that. Let's I don't know, explode some bombs in the stratosphere because it might be good. Just an experiment. Yeah. So there are sometimes high stakes, and then you try whatever. Anyways, what are we talking? Okay, so we're discussing a bunch of things, but we were not discussing yet the solution techniques. I mean, okay, so we said, okay, plug-in method. So we have an MDP. Oh, you use any method to solve it. Like policy iteration, we know it's like going to be poly time. Solving it, it's all good. And we read out the optimal policy for this. I put a hat on the top. I put a star in the hat. Oh my God. Okay, and then we want to say that this is not bad compared to this other one. So that is the value function of the optimal policy. And okay, so there are multiple schools. So there is the school with the hat. So maybe I'm going to follow the school with the hat, and there is also the school with indexing with models. So you could write, V pi, V hat pi, or Vm pi, and Vm hat pi, stuff like this. So if you subscribe the school with the hat, then you're not writing these indices. In the other case, you write the indices. I'm switching back and forth, so I couldn't decide which school is better. Anyway, so this is the optimal value function in MDPM. We care about whether the value function of our policy when we run it in M, is close to it. It's going to lose something, so it's going to be below it, so we need to upper bound this. Right? So we want to know how big is this. And somehow we want to relate it to the first approximation to the modeling errors. So these differences between P and P hat and R and R hat. So we can forget about how we came up with P hat and R hat and just ask this question. How do we do this? And then there are two line of thoughts. Use the value difference identity. And the other line of thought is that, I don't know, compare Q star and Q hat star. They shouldn't be too far from each other. So Q hat is the optimal action value function, Q hat star. Optimal action value function for M hat, Q star is optimal action value function for M. So this should be closed. Therefore, pi hat which is greedy with respect to Q hat star is going to be a good policy. We already had seen a result like that was saying that if you can approximate well the optimal action value function and you choose the policy which is greedy with respect to this approximate thing, it only loses the difference times the horizon, right? The difference between Q star and Q hat star. Okay. Time's flying. So I'm not going to go through any of this, but there are lessons to be learned about both of them. So this has some beauty because here you will see that this relates to how close P and P hat are. So you can relate this to this times H squared. So there is a quadratic dependence on the distance between P and P hat. And then here, we know that the loss that comes from choosing a greedy policy with respect to this approximate action value function is H time Q star minus Q hat star. And so now if we plug in everything, then we get an H cubed. But along the way, there are nice things happening because it's like easy calculations. So this is really easy calculations. But there is an H cube that comes from here. The value difference identity brings this down to H squared without any further ado, except that you have to use all kind of ugly covering arguments. And then, okay, so at this stage, if you have this design where you can control how many samples each state action pair receives. Let's say each of them receives n. Then these differences are like 1 over root n. Then here the error is the dominating term seems to be like this. And here it seems to be like this. And so the critical sample size is that comes from here is something like this. And here it's something like this. Sorry, to the power of 4. And so we see that, okay, this has one more step, one more triangle inequality or something. And so it's not an ideal way of doing things. This has one less. Using the value difference identity, just like it's more direct. It's just arguing more directly about these differences between the value functions. And because of that, you immediately receive an h factor, which saves h to the power of 2 in the sample complexity. And then you can ask the question, is this optimal? It turns out to be not optimal. So if you prove a lower bound, then the lower bound happens to be h cubed over epsilon squared, and then there is an SA. There's maybe some log terms, not in the lower bound. And here, if you're not careful, then you can get an S squared. So that's like some covering arguments tend to bring in this additional S. Remember, we were getting this S from here. So whenever you resort to saying that, oh, the one norm, in one norm, these two distributions are close to each other, then you pick up an extra S factor. The way to avoid that is not to go for a union bound like this, but somehow keep a function here, which is a deterministic function. Cannot be a random function, because if it was random, you would need covering arguments. Then you again pick up an S. And this can do that. This can do that. So here you can massage things in such a way that like you have just deterministic functions that multiply these kernel differences. And here it's just not working. But you can still get rid of this with some additional cleverness, and you can replace this with cube with some additional cleverness. We are going to talk about these next time. And we've absolutely run out of time. Do we have questions?
We have one.
Oh, okay.
Do we have time?
Sure.
Yeah.
I mean, I do have time, but
Oh, okay. So,
It's fine.
my question is about the assumptions that you had as like prerequisite for the whole like proof on the upper bound. So, in the lecture notes, you mentioned that we assume that the whole thing is finite and like the state action space for both n hat and n are equal. So my question is that, like, let's assume that we have like some kind of data we collected based on some kind of policy, and then we train a neural network with like some kind of parameter theta or gamma, whatever, on that data. So the state action space for that m hat or that MDP simulator, like the one that we learned with neural network, could be not completely, but could have some different states, for example, or different actions from the original one. So they could be not equal to each other. My
that
question
sounds pretty messed up if the action spaces are different, right?
So yeah, but like it's possible, like in practice, when we are using, for example, neural network to learn
How would that happen?
that batch of data, then our MDP model would be different in terms of like state actions, and then it will affect the like that transition probability and like maybe that C over square root of n s and n and then the whole thing might change, right?
Okay.
I'm asking how it will change everything. Like, is it possible that we come up with still like an upper bound in those cases that we have some kind of error on state action spaces, PT and stuff like that?
Yeah, I think it's a valid worry that you could have situations where your approximate model doesn't share the state action space with the true world. There are different levels of difficulty with this. So for example, if we have extra actions here, and the policy we derive is using those actions, how are we going to employ or deploy this in the true world? If you cannot translate it back, we just don't. Like, we can't reason about this thing, right? Like, there has to be a way. So otherwise, we just like did something, we imagined that we can do an action, let's say, fly to the moon, right ag. I solved the problem. Hey, I'm so energy efficient, but like, okay, like, no, let's deploy this. Well, I'm sorry, that action is missing, so that's highly dubious. So I don't think that that happens on their own.
Maybe the policy we come up with, when, for example, an action is missing, is like the best sequence of policies that can approximate the original like missing policy, for example, like the original missing action, for example.
I think if you can make up actions, if those are still rooted in actions in the original MDP, I'm totally with you. Because then I can translate and I can use the policy. Ultimately, the goal is not just to bound differences and whatnot, but to use things. So I came up with this M hat. I really need a way of using the policy that I'm reading out. So there has to be a translation that just helps me to execute whatever the policy is telling me. If that is a way, then you can somehow piggyback on the top of this, and the difference in the action space is not going to matter that much. So then you can patch up this whole procedure to do this. And the state space, that's pretty much the same. I think I would even say that, okay, here we are pretending that we're in this small tabular setting, we're counting, but like, we do this only for the sake of getting inside. Of course, no one in their sane mind would ever do anything like this. You would never discretize, you would like, that's like, it's like unimaginable that someone would try something like this on a real problem of an interesting size or structure. So people don't do that. They come up with all kind of models, like a neural network is modeling the dynamics. The state is not even explicitly modeled. Doesn't really matter. Like, normally it doesn't matter. Like, the features that are hiding the states and the actions, you can just think in terms of that. For this analysis, yes, it does matter. So you can't run this analysis without mentioning states and actions. That doesn't mean that. So I think that these analyses have a grain of truth to it, to the degree that even if you're not doing this discretization, when you're learning a model, it's kind of going to be very similar to this. So let me, okay, so at one point here in the analysis, like all these analyses that I was not showing today, it doesn't care about whether the state action pair is finite. It doesn't care about whether you're modeling it proper or one is bigger or smaller. It cares about these operators, the differences between the operators, and whether you can map the policies. And so you can push this a long way, and you could apply the same analysis to say that, oh, well, I learned the dynamics with a neural network. If the dynamics is faithfully representing the true dynamics in such and such a way, then everything is fine. At one point or another, you have to somehow say what you mean by that the two dynamics are the same, where you're going to face the dilemma of like, okay, are we naming states now or are we not naming states? Maybe you only name functions of states, and that's all fine, right? Like, if on functions of state they are behaving identically and the policies only depend on these functions, the same functions of the state, so some states are put together, it's all fine. Like, all the math goes through. So, what's the morale? I think, well, this is a caricature analysis for the purpose of understanding how you do the analysis, what are the factors that do matter, and how do they influence the outcomes. But you can generalize it to a great extent. And a lot of parts of the analysis are absolutely not tied to this. At the same time, I would again mention that if you deviate from the action space by introducing additional actions, you should only do that if you know how to execute those actions in the actual world. And if you know that, then you just conservatively extended the action space. So that it's like you created macros or something like that. That's fine. You can imagine that you would do that here as well, and then know you have the same action space. Even though those actions were not listed there originally, you could still list them. It wouldn't change much because the values are not going, the optimal value is not going to get better if you introduce actions that are only using actions which already existed. It cannot improve things. So in a way that's all good, and maybe that's why you could almost without loss of journey just say that these are the same, because you can do all these steps. By the way, in imitation learning, this is a much bigger problem, because I have my robot, and my robot can move such and such, and my action space could be very different. So for example, if you do imitation learning by, let's say, humanoid robot, and it would need to walk like a human, but my body is different than their body, so copying my movement to their movement is absolutely non-trivial because of this. And that's an action space difference, that's a state space difference. Now you have to map everything, and it's a fun problem.
I was hoping that maybe if we like define everything as like a parameterized function, like S as a parameter of, for example, theta, or S and A parameter of theta and theta hat, then all those like estimations of C over, that would also be a function which can be controlled, like eventually all the boundaries
Sure.
could be controlled with like a parameter of theta, and then
Sure. The only issue I would take is that like this SA is like I wouldn't mess around with that.
is there any specific reason like that you're worried about S? Because like I imagine like it's similar to A. Like you can, for example, have like extra states in your M hat, like MDP, which are not real, right? Like they are not in that.
Right. Imagine
function.
states or whatever.
Yeah, but they can mess around with all these like value functions and action value functions. But maybe to some extent, maybe like we can somehow use some of these parameters like theta, and then put a boundary in.
Good. So we have the original SA. Maybe we have SA hat or something,
Yeah.
right? At the end of the day, we do our computation. We design a policy pi hat, but we want to deploy it. So what does the policy do? Policy takes a state, returns an action. Deploying a policy in this other word would mean that, okay, lucky for us, if you observe the state, there is a state that's coming out, S, and now we have to find some state here, because otherwise we won't even know, like, like policy being applied, what does it mean? So there has to be some mapping, I don't know, I'll call it F, that maps this into some state S hat. And now the policy can pick the A hat, so it's picking some A hat. And similarly, there has to be some translation that translates it back to some A. And then you can deploy. So the minimum requirement for the deployment is that this interfacing is possible. Once you resolve this interfacing, the theory is not going to change much.
Interesting. And one last question. In terms of like actions being inequivalent to each other, and like this patching idea of like we could patch one action in one for the other one. So has anybody ever approached this problem to like get into option models and stuff like that?
Yeah.
Is there
I think a
anything-
lot of people are thinking about this.
No? Or yes?
Yes.
Oh yes?
Yes.
Okay.
Yes. I mean, so when people are thinking about the action models, that's really extending the action space and also maybe changing the dynamics and switching to some EMDPs. So it's like all kind of other complicated stuff is happening, but it's basically patching the action space.
Okay, so the fundamental of all those like proofs is similar to what
Yeah.
we do. Okay.
It would be. Yeah, good points. Good points. So when people a lot talk about state abstraction, action abstraction, this is kind of the picture that should come to mind. All right. Okay. I guess see you on Monday.